Hello, Physics 110 students. I got a good question here from the homework number 3 in our 2D motion. It's number 27, and haven't had a chance to make that video, so I thought I would make it. The question really centers around the hardest part of this problem, which is part D. But let me build up to it. So I will go ahead and do an A, B, and C, even though that wasn't the question, but just to make the video complete, if anybody else might be struggling with it. But yeah, D is really kind of a hard one. And let me use this as an opportunity to remind you, I think one of the strategies that can really help is that divide your paper into 2 pieces, and so that you'll have all your calculations of your X motion on one side and all your calculations to the Y motion. And ultimately, we got to put those together, and that's what step D is here. But if you read this problem, and maybe I should have done my calculations over here, so I'll do this. So I'll do my calculations over here. But just drawing a picture, it says a ball is thrown horizontally from the top. Let me just use this as the cliff edge. Okay, so here's the top, and here's a ball, and we're going to throw it horizontally. So a ball is thrown horizontally from the top of a 60-meter building, and it lands 100 meters from the base of the building, and ignoring air resistance. Okay, how long does it, how long is the ball in the air? All right, so applying this whole idea of projectile motion, that is, we can apply these equations of constant acceleration to the X components, the X motion, and the Y component. And that's why I like to take a piece of paper and just divide it in half so that I can calculate stuff involving horizontal motion in one column and stuff involving vertical motion in another column. Now, I'll emphasize, going back a chapter, that these equations, or this equation, it's actually one equation, just this one's being applied to X and this one's being applied to Y, are only valid for constant acceleration. And so let me make a comment about that. For something flying through the air, we like to say gravity is then affecting it downward. It has a negative 9.8 meters per second squared. And it's only in the vertical direction. And so that's why I'm going to say here that the acceleration in the vertical direction is a negative 9.8, but the acceleration in the X direction remains 0. And this might be a chance to repeat. The reason I made these 2 columns is because the way we do 2 dimensions, now for that matter 3 dimensions, is we just do 1-dimensional motion twice. Okay, and so all that good stuff that we developed in chapter 2, we're going to extend here into chapter 3. We're just going to do twice. So we do a motion X and motion Y, and that's why the 2 columns make sense. And hopefully that's what will make chapter 3 kind of easy to comprehend, because we're just going to be repeating here in chapter 3 what we did in chapter 2. It's just twice, one for X and one for Y. And we're going to have an acceleration separate for each of those. Now, coming to A here, A says, how long is the ball in the air? And so the ball's motion, of course, is going to have a horizontal and a vertical all at the same time. But I'm hoping you kind of see, and if you don't, you can kind of see it as you play around with the equations, that the amount of time in the air really is determined by the vertical height. And so it's just going to keep doing its horizontal thing until it runs out of space, if you will, because then it runs out of time as it falls down. So that's why I'm going to go ahead and do my first calculation right here. And so I'm going to look at this and say, okay, in my little picture, of course, it kind of depends where you put the origin, but why don't I just put the origin right here where the ball gets launched? And so I'll say its final position is at negative 60, and it's starting at 0. And so in a vertical motion, it's going to start here at 0. And while it's going across to X, it drops down in Y. So only looking at the Y motion, it's going to finish right down here. Of course, way over here on the X-axis. So its final position is negative 60, and its starting position is 0. Now, its initial velocity in the vertical direction is 0. And here's where we have to make sure we kind of understand the physics of the problem and not just kind of blindly plug and chug into the math. We got to say, okay, what really happened here? And what really happened is we threw it horizontally. We threw it with just a horizontal velocity. So that means this initial velocity in the x direction is some number. I'll just say number. But it has 0 going up and 0 going down. Now that will soon change because gravity will pull it down. It's going to gain an acceleration in the y direction. But at starters, it's 0. And so that's why I put here for this first term 0. And then I will put the acceleration of negative 9.8. And now you can see the only unknown in this problem is the time, and that's perfect. So why don't I do this? The negative 60 here, together with that negative, make a positive. Bring the 2 over, and so that makes 120. Divide it by the 9.8, and I get time squared. And then finally hitting the square root button will give me the time. So grabbing my calculator, I have 120. I divide it by 9.8. That's the time squared, taking the square root of all that, and I get about 3.5 seconds. So 3.50 seconds is the answer to A. How much time did it spend in the air? Okay, so continuing on, it says, what must be the initial horizontal component of the velocity? So again, notice the question's asking about horizontal motion, so I'll do that calculation over here. And as I look at the picture, it moves over starting at x equals to 0 and comes all the way over to x equal 100. So again, while it goes over 100 in the x, it drops down 60. That's why it ends up over here. So in this part of the equation, I'm going to say final is 100 and initial is 0. And I'm looking for this. This is the question. What was the initial velocity in the x direction? And as we said earlier, it's some number. I don't know what it is. Now the time is where we can come over to the vertical motion. So that's the stuff that, or the time is the scalar that it can go back and forth between each of these. In other words, the time it takes to drop down, and the 60, and the time it takes to move over 100 is the same amount as 3.5 seconds. So when we figured out that it was 3.5 seconds to drop down, we were also saying it was 3.5 seconds to move over. And as we mentioned earlier, gravity pulled only down in the y direction, nothing in the x direction, so there is no increase or decrease of speed in the x direction. And so again, you can kind of see here that the only unknown would be that initial velocity in the x direction, which, by the way, without any acceleration, it's also the final velocity. And in fact, it's also the x velocity at any time during the flight. So this would be 100 divided by 3.5. So 100 divided by 3.5 is about a 28.6. So 28.6 meters per second would be the velocity in the x direction, not only initial, but also final and everything in between because no acceleration. All right, so that would be the answer to B. C, what is the vertical component of the velocity just before the ball hits the ground? So again, notice it says vertical component. By the way, also notice it didn't say what's the final horizontal component. I'll put that here. Final speed in the x direction is also the 28.6. So I'm sure that's why the author did not ask for it, because it just seems so obvious because you put acceleration is equal to 0. Although this is really the heart of the question I got, because I need that number right here to answer part D. So I thought as long as I was working on X, I'd put it. But I really need to go back to this column and write out equation number 1, which says final speed in the y direction is equal to initial speed in the y direction plus the acceleration in the y direction times time. And this part C is asking for this. What is the final speed in the y direction? So in that y direction, right, is it right there? And I should be careful when they say, final speed, they mean just before it hits the ground. Because once it hits the ground, then the ground pushes back and the speed changes dramatically. In fact, we can't do it with this calculation because we don't know what the acceleration is once it hits the ground. This acceleration only applies because of gravity, and so it applies just to that moment, microscopically or infinitesimally, right before it hits the ground. And so it says vertical component just before the ball hits the ground. And as we mentioned earlier, the velocity in the y direction initially is 0 because, as I said over here, it was thrown completely horizontal, nothing up or down. There's no angle to it. It's not slightly down or slightly up or even a lot up. It's none of those. It's completely horizontal. And then, of course, the acceleration is at negative 9.8 meters per second squared to make my units right. The time, as we've already done, is 3.5 seconds, and so this should give me a downward speed, so there's the negative, so 9.8 and times 3.5, and so there's a negative 34.3 meters per second. So this ball, and I don't know if my picture's showing it real well, because my picture kind of looks like, at this point, it's just going straight down, but as we said, it doesn't change its horizontal speed. So actually at this point, it's kind of angled a little bit. So maybe a better picture might be like this. And right here, it's got a certain amount down. So that's this number. And it's got a certain amount over, and that's this number. And this problem, it says, what is the velocity? See, notice it didn't say what is the horizontal or the x or the vertical or the y component of it. It asked for the whole thing. So including both the horizontal and vertical components of the ball just before it hits the ground. So they want us to put these two together. That is, what is the total motion when you include both of them? Now, there are perpendicular motions to them, and so if something moves down and at the same time moves over, then we can draw a little triangle representing a combination of down and over. And of course, remembering Pythagorean's theorem, which says the sum of the square of the legs equals the square of the hypotenuse. So we need to kind of understand our vectors, and that's what makes this number D or letter D kind of hard, is because this is going to be your challenge. This chapter and the next couple of chapters is to making sure you're breaking things into its components. Things are going to be two-dimensional. Things are going to be moving X and Y at the same time. We're going to push on things at some random angle, and so it's essentially to pushing it both X and Y at the same time. And so how do you combine those together? And since they're perpendicular to each other, we say we combine them. We don't want to say we just add them, because I don't want to just add these numbers. I want to combine them to get their equivalent strength when they're put together. And I don't just add them or subtract them. They're at right angles to each other. So we add them. A fancy word is calling, we add them in quadrature. We do the Pythagorean theorem. We say if we have this much in the vertical and this much in the horizontal, call that A and B, then we want to know the combination is the two of them together. It's a hypotenuse of a triangle. So that's where I'm going to say something like this, that the final speed total squared is really made up of the final speed in the x squared and the final speed in the y squared. And so the sum of the square of the legs equals the square of the hypotenuse. So taking the x squared would be 28.6, and I'll square it. The vertical is the negative 34.3, and I'll square it. And that will give me the velocity squared. And then so whatever I get, I need to take the square root of that to get the total answer to this problem. Okay, so grabbing the calculator here, let me go the 28.6 and square it. And add to it the 34.3. And if you don't mind, I won't bother to do the negative, because once I square it, that goes away. And so that's the speed squared. And now taking the square root of that, looks like about a 44.7. So 44.7 meters per second is the effect. That is, if you were measuring some distance along here, it would be 44.7 meters in that 1 second. That's a combination of moving down 34.3 meters in 1 second and moving horizontal 28.8 meters in 1 second. And I think technically we can stop there, but they do say velocity. Well, so maybe we can't technically, because velocity means a magnitude and a direction. Oops, velocity. Magnitude and a direction. So I suppose to be complete, I should put direction. I think that's what the author wants. And I want to show you anyways whether the author means it or not here. So let me finish this by saying, okay, we could look at maybe this angle here. Oh, I guess we could also look at this angle. Maybe that would be a better angle, looking at this one, because this one we would say it is at some angle down from the horizontal as opposed to outward from the vertical. Yeah, so let's do this one. And in fact, because I'm going to do this one, why don't I redraw this triangle? So I'm going to put this here, triangle, because I had this piece, which I called A, and this piece, which I called B. And so that's this little triangle. But now I want to find this angle. So let me draw the horizontal first and then the vertical. So horizontal first is the B and the vertical is the A. Because going back to my math class, or maybe reviewing some math, in fact, maybe I should make a review of trig, because you guys have been exposed to very little trig. And so there are three important functions. If you call the hypotenuse C, there is the sine of an angle, there is the cosine of an angle, and there is a tangent of an angle. Okay? So when you take the sine of an angle, you go the opposite over the hypotenuse. So this would be A over C. And when you do cosine, you do adjacent to the angle over C. So this would be B over C, the hypotenuse. And the tangent is the third option, which is the opposite A over B. And what we want to find is the angle. And so we need to know either the A and the C and use this function, or the B and the C and use the cosine function, or the A and the B and use the tangent function. And the truth is we know all three of them. So any of these would work, because this was the X motion. So this is the B. This is the Y motion. So this is the A. And this is then calculated from that. So this is the C. So again, all of these would work, but I think maybe I'll just grab the tangent one, which will take me back to these two. And I really don't have a reason why that one's better. I can't say which one is better, because there's no reason I can't use that for the C down there. I just feel like I might have made a mistake in here, and so I'm a little leery of the C, but I could have made a mistake here for that matter too. So don't have a good reason other than it's further up in our calculation, and so it's more likely to be right than these, because I could have gotten these right and then this wrong. But anyways, I'll keep with the math here and finish it up. Actually, just to save me a piece of paper, I'll come back to here. So I'm going to write this as tangent of theta, and I'll just copy A over B. But as we said, the A is the vertical piece, so this is minus 34.3. And then the horizontal piece is the B, that's the 28.6. And why don't I start there? Because, like I said, some of you have very limited experience with these trig functions, and that makes me think I should make a little math refresher here. And I think I will do that later on. But let me just kind of show you for the tangent function. All we really need to do is just use these buttons here on the calculator. That's what we're going to do, the sine, cosine, and tangent. And then they're inverse operations. So the second function, inverse sine, second function, inverse cosine, and second function, inverse tangent. So watch, if I take the numerator, which is negative 34.3, and I divided it by the 28.6, all of that is this negative 1 point, and looks like it rounds to a 2, 0. So what you're saying here is take the tangent of some angle, and that's what we'd like to find, and you get a negative 1.20, okay? And on a calculator, to undo it, kind of like an inverse, well, like square and square root are inverse functions, and so you undo them with each other, or you have the log and the exponent, they undo each other. So to undo it, we use a function called the arc tangent, sometimes referred to as the inverse tangent, although that can be misleading because inverse tangent is a reciprocal, and that's not what we mean in that phrase. But this are inverse operations. They say if you have some angle, take the tangent of it and then take its inverse. So you get back to just tangent. They undo each other. It's like saying start with the number 5 and square it, you get 25, and then square root, you get back to 5. Okay? So they undo each other. And so that's what we needed to do to get our equation to say theta equals something. So in this case, I'll use my calculator and go second, and right there in the blue where it says tangent inverse, I'll hit that and see there's the operator, the tangent inverse. So we're going to take the inverse tangent, or a better phrase is arc tangent, and I'll just put last answer. Okay, and then hit enter. And I guess I should have checked, am I in degrees? Yeah, okay. And so this looks like it's angled down, there's the negative, and 50.2 degrees. And so that's the hard step, get the magnitude of the velocity and the angle down. All right, hope that helps someone. Take care.